Hey everyone, for our CX4240 final project, we chose to look into using machine learning to predict which teams will make it to March Madness and how they will finish. Every year, millions of people create brackets with who they predict will win the tournament, as well as each game. Websites such as ESPN and CBS Sports offer grand prizes to those who finish in the top percentile for their predictions, and many friend groups or office groups put together pools where the top finisher wins a reward. However, a perfect bracket has never been predicted due to unexpected upsets every year. While predicting a bracket is monetary motivation for ourselves, predicting if a team will make the tournament based off of statistical variables will also offer insights to coaches about what they should focus their tactics and training on. Our main goals for this project are to first predict if a team will make the tournament, then predict the outcome of the tournament or where the team will finish. Originally, we wanted to use our model to predict the tournament bracket for 2020. However, COVID-19 has caused the tournament to be canceled for this season, and we could not find any up-to-date data sets to create a theoretical bracket either. We selected our dataset from Kaggle, and it includes data from the 2015 through 2019 Division I college basketball seasons. It has 23 features for every team, all listed here on our webpage, along with descriptions of what they are. These features include things like shooting percentage, seed, where they finished in the postseason, turnover rate, wins, etc. We also added our own feature called win percentage, which we calculated from the wins and games features. We compared the average value for each of these features for teams that made the playoffs versus didn't make the playoffs in the 2015 through 2018 seasons. This chart can be seen here in Figure 1, and you can see that there is the most variation between class for ADJOE, which is the adjusted offensive efficiency, ADJDE, which is the adjusted defensive efficiency, BARTHAG, which is a power rating that describes a team's chances of beating an average Division I team, WAB, which is wins above the bubble, or a score that reflects the expected win percentage and then the actual outcome of a game, and then win percentage. This led us to wonder if these variables might have the most influence on whether a team makes it to playoffs or not. This project used supervised learning to predict whether a team would make the tournament and where it would finish in the tournament. Originally, we set up our models as logistic regression classifiers and planned to compare those results to other models to choose the best one. We planned to choose the best model based on cross-validation score averages and used F1 score instead of an accuracy score, since F1 score tends to be a better indicator for unbalanced data like ours. We tested 6 different models: logistic regression, Gaussian naive Bayes classifier, support vector machine, random forest classifier, extra trees classifier, and linear discriminant analysis classifier. So on to the first problem, predicting whether a team will make the playoffs. We trained this model on the 2015 through 2018 seasons for all teams and used the 2019 season as our test data. The postseason feature originally included where a team finished, NA if they didn't make it, so we converted it to a binary feature for this model, 1 for teams that made playoffs and 0 for those that didn't. Next came variable selection, which we did by utilizing an extra trees classifier. We dropped year in conference, fed our data through, and as you can see in Figure 2, WAB, BARTHAG, win percentage, ADJOE, and ADJDE were the most influential features for classifying our data. We dropped all other features from our data and then ran it through our logistic regression model. We ended up with a significant number of false negative predictions, so we evaluated all of the other models and saw the results in Figure 3. Random forest classifier had the best performance score, followed closely by logistic regression, and then extra trees classifier, so we decided to move forward with the random forest classifier. While this model went ahead and predicted whether a team would make playoffs, in real life every conference has its own tournament, and the winner of each conference, 32 total, receives an automatic bid to playoffs. A selection committee then hands out the remaining 36 bids as they see fit. To simulate this process, we calculated the predicted probability for each team of being classified as a 1, then selected the team with the highest probability in each conference to represent the conference tournament winners. We then chose the next 36 highest probability teams out of the remaining pool. What we found was that our random forest classifier model achieved perfect accuracy and F1 score on the training data that it learned from. When we ran it on the test data from 2019 without the adapted selection process just described, it achieved 93% accuracy and an F1 score of 0.82, but it also only predicted that 59 teams would make playoffs when really 68 teams go. After we added our adapted selection process, the accuracy and F1 score remained the same, but it ensured that 68 teams would be classified as making playoffs. The model misclassified only 24 of 353 teams, and the confusion matrix is shown as figure 4. The model made 12 false negative and 12 false positive predictions. We expected consistently strong teams such as Duke and UNC to make the NCAA tournament, and our model did assign teams like these probabilities greater than 99%, essentially guaranteeing that they would be classified as making the tournament. Many other expected teams that make the tournament most years, like Gonzaga, Villanova, and Louisville, all had very high probabilities of making the tournament as well. So where did our misclassifications come from? A table of the teams that were misclassified are shown in the table below, along with their conference and postseason, which is where they actually finished, and then prediction is how our model classified each team. We can see 6 overlaps occur based on conference: MAAC, MVC, NEC, SC, SUM, and SWAC. We found that the teams in these conferences with false positive classifications were top teams in their conference and therefore expected by our model to win their conference tournament. Meanwhile, the teams that were false negative classifications in the corresponding conferences were the actual conference champions and generally a lower seed in their conference tournament, indicating that an upset occurred in the conference tournament, leading to the better teams missing out on the tournament. Additionally, St. Mary's, Oregon, and St. Louis were big upsets in their conference tournament as well that year, taking spots from teams that were on the bubble of taking one of the at-large bids. Other misclassifications may be attributed to the fact that the at-large bids are decided by committees, which can lead to a little bit of bias.
After determining which teams will make the NCAA tournament, next we want to try to predict the outcome of the tournament. Similar to the first section, we also used the 2015 through 2018 seasons as our training data and the 2019 season as our test data. Additionally, we added each team's win percentage as a feature and dropped the wins in games features. However, this time we did not convert the postseason feature to a binary variable. Initially, we created dummy variables for each conference, but soon realized during variable selection that none of these variables were ranked above or even near the other original features. Therefore, we did not include these variables in our model or variable selection. Similar to last section, we wanted to perform variable selection to determine which variables would be most important. The results of the variable selection are shown in figure 6. As we can see, none of the features had a much larger value of importance, with all features being within 0.04 of each other. Therefore, we will not remove any features and will use every feature when making our model. One important note, however, is that when the variable seed is used in creating our model, it tends to overvalue higher seeds and not predict many upsets occurring, which is an integral part of March Madness. To adjust for this, we created a new variable to track how well a team performs in the tournament relative to its seed, called wins above seed, or WAS. For example, a 1 seed would be expected to make it to the Final Four, a 2 seed to the Elite Eight, and so on down the list. However, if a 1 seed were to be upset in the first round, as Virginia did in 2018, they would receive a WAS score of -4 due to losing 4 rounds earlier than expected. Similarly, if a 5 seed were to somehow make it to the Final Four, they would receive a WAS of 3 for performing 3 rounds better than expected. Additionally, we would add a bonus for making it to the finals, and then another +1 if they actually won the tournament. Using the WAS for the entire data set, we calculated the average based on the seed to create a new feature that would help balance upsets and higher seeds still being expected to win. After adding this variable, we perform model selection by using cross-validation to compare F1 scores as mentioned in the methods introduction to select from the various modeling methods we introduced. While we originally planned to use logistic regression to model teams' performance in the NCAA tournament, our F1 scores indicated the linear discriminant analysis model was the best with an F1 score of 0.477, followed closely by Gaussian naive Bayes classifier and random forest classifier. From this information, we decided LDA would be the best for predicting teams' outcome in the NCAA tournament. While this model went ahead and predicted the actual classification of a team's finish in the tournament, we realized that more teams were being classified into certain categories than were allowed, such as there being 2 predicted winners. To adjust for this, we took the probabilities of being classified into each category plus the probability of being classified into higher categories to select the best team for each postseason spot. This allowed for the correct number of classifications for each tournament finish. The LDA model achieved an accuracy of 0.67 and an F1 score of 0.66 for our training data and an accuracy of 0.54 and F1 score of 0.53 for the test data before making any of these adjustments. After making the realistic adjustments, our accuracy and F1 score increased to 0.56 and our total misclassified points were 30 out of the 68 teams. Below is a confusion matrix, and as we can see along the diagonal, we can see when teams were correctly predicted and anything outside of here were incorrect predictions. This seems to show poor performance of our model. However, a bracket isn't viewed as being good based on predicting precisely where each team finishes. These scores fail to account for teams that overperform but still technically made their finish, such as a predicted winner actually only making it to the Final Four. They still made it to the Final Four, but didn't advance as far as being the winner. Additionally, while our bracket would probably not win Warren Buffett's grand prize for being perfect, a bracket could have still performed very highly in the top percentile, as some bracket pools a lot more points for predicting accurately in the later rounds than the early rounds. To illustrate this, we have created our hypothetical bracket for the 2019 tournament by selecting the highest probable team to make it to each round and adjusting for any anomalies, as our model did not take into account region limitations, such as our model saying Texas Tech and Gonzaga making the Final Four, which is impossible due to them being from the same region. So we took the team that had the highest performance in the later rounds. As we can see, our theoretical bracket actually performed fairly well. It had a lot more accurate predictions shown in green than red. While we incorrectly predicted the national champion with Gonzaga, we predicted every Sweet 16 team correctly, even a 12 seed Oregon making it, and also predicted the Final Four half correct and 7 out of 8 of the Elite 8 teams. We correctly predicted Auburn, a 5 seed, making it to the Final Four, which was not expected going in. As we can see, the predicted bracket actually correctly predicted 51 out of the 63 games, giving an impressive 81% prediction rate, which indicates a lot better performance than the original 56% accuracy. However, depending on the contest, like I said, some contests weighed the later round predictions heavier than the earlier rounds. Using ESPN scoring metrics, our bracket would have gained 61% of the total points and put us in the 94th percentile compared to all other bracket scores, which is extremely better than the 56% accuracy and would likely lead to prizes and smaller pools with friends and coworkers. By using cross-validation to select the model, we found Random Forest Classifier to be the best model to classify which teams make the NCAA tournament, and the Linear Discriminant Analysis Classifier was the best model to classify teams to predict where they finish in the tournament. We found misclassifications in predicting if a team makes the tournament are likely due to upsets in conference tournaments, leading to worse teams making the tournament. This shortfall is due to the fact that these conference tournaments are unpredictable in the same way as the actual NCAA tournament. Caution should be used when making overarching assumptions on these results, as the dataset was only 5 seasons and the predictions were only for the 2019 season. Future work to improve these models include using a larger dataset, more intricate machine learning methods, and possibly focusing on game stats and over an entire season and using that specific season's game stats to predict each game in the tournament to predict how the tournament would unfold. Additionally, to make better recommendations to coaches on how to improve their team, a model to predict wins would be more beneficial in determining important features instead of a model that predicts making the postseason based on many factors revolving around wins. Ultimately, we were looking forward to trying to predict the 2020 NCAA tournament with our model, but we sadly were not able to due to COVID-19's impact on the world.